Is my screen visible?
Yes, sir.
All right. Okay. So last class we looked at the complete derivation of the rigid body kinetics, and we understood what are the implications, what is the expressions for these so-called Coriolis matrices and mass matrices. We looked also at the idea that there are multiple representations possible. So multiple representations are possible for the CRP matrix. And then we also understood that there is one particular form which really does not depend on the linear velocity, which may really be useful when we want to consider or handle ocean currents as well into our equations of motion. So for that case, we know that the CRB matrix really doesn't depend on the velocity, is very helpful property, and we kind of put it off saying that we are going to look at that derivation of the equations of motion with the current at a later point of time when we talk about the modeling of the ocean currents. So that is where we were yesterday. So let's continue forward today. So today what we are going to do is we are going to start talking about other forces which come into the play in the dynamics. So this generalized tau, which is representing the generalized force acting on the rigid body, we are going to kind of take some components of these and start looking at what those components are. Can we give them a better representational form and include them into our dynamics? So we'll start looking at how to make this model much more rich and suitable for our purposes, especially with respect to ship dynamic positioning models. What are all the important dynamics which we need to consider? Okay, remember that the mass matrix is a symmetric matrix. We had already seen this part, and the CRB matrix can be parameterized as a skew symmetric matrix when we consider the nonlinear Coriolis matrix. Remember that when we actually linearize this, we get something called as CRB star, and we saw that that matrix is not skew symmetric. So this one is not skew symmetric. All right. So let's kind of start working more into our maneuvering modeling dynamics. So before we do that, we have to understand that when we talk about maneuvering, we're really talking about more about the horizontal plane of motions, so which we are meaning that surge, sway, and yaw. That is what is of more interest to us. Sometimes you'll also have a roll included into the surge, sway, and yaw dynamics, just so that the stability issues in the roll, if at all they are getting affected due to the horizontal plane modes, due to the modes of motion in the horizontal plane are affecting roll, in which case we might want to consider a 4-degree of freedom model. But typically you would like to see that this will be a 3-degree of freedom model, especially when we are dealing with surface vessels. Surface vessels or surface vehicles. When we are dealing with underwater vehicles, you probably would need all the 6 degrees of freedom. So you will need 6-degree of freedom models when we are looking at underwater vehicles. That is because that here all the modes of motion are maybe relatively large, so you may actually pitch by large angles, you may actually roll by large angles, you may experience an increase in depth as your AUV tries to submerge itself. So these modes now start to play a coupled dynamics, interact with each other through the coupled dynamics. So there we can't go away with a 3-degree of freedom model, and we would really require a 6-degree of freedom model. But when it comes to surface vessels, we know that generally the roll, pitch, and yaw. But the roll, pitch, and heave are relatively smaller compared to the magnitude of the motions you observe in surge, sway, and yaw. So therefore, we can get away with a so-called 3 degree of freedom model, and we are looking at surface vehicles. So let's try to understand what happens in a 3 degree of freedom model. So in a 3 degree of freedom model, we saw that this generalized velocity vector will be given by u, v, and this is wrong. This should be r. Okay, so which is the yaw rate. And eta would be given by x, y, and psi, where psi is the heading angle of the vessel. So generally, for a maneuvering ship or a semi-submersibles or offshore structures, there is symmetry about the XZ plane, which means that generally if I have a vessel such that this is the x-axis and the y-axis is this way and the z-axis is pointed down, then you know that there is a symmetry in the XZ plane, so that the ship actually looks like a mirror about the XZ plane. So in that case, we will have some simplification of our mass moments of inertia. Similarly, if you have offshore structures, you will typically find them to have a, what you call, two planes of symmetry. So if it's an offshore structure, you may have something like this, where columns are coming out and then there are pontoons connecting these columns. So you may see that here there is an axis of symmetry this way and an axis of symmetry this way. So there you might have more axis of symmetry, but typically an XZ symmetry definitely exists, whether it be for ships or offshore structures. And so therefore we will find that any of the terms other than IXZ and IZX will typically turn out to be 0 because they will have a contribution due to these Y's, which will be symmetric about the hull form and will lead to 0. So IXY is equal to IYX is equal to IYZ equal to IZY. All four of those will be equal to 0. So which simplifies our 3 cross 3 mass matrix as we see here, which would be simply be characterized by M0, 0, 0, M, MXG and 0, MXG and IZ, where IZ is the second mass moment of inertia about the z-axis. All right. So if I look at what is the simplification which we get to the CRB matrix, which is the Coriolis and the centripetal matrix, it can be seen that when we are looking at a Coriolis matrix, which depends on, and we are here only interested in keeping so-called to the first 3 modes or the 3 modes, which is surge, sway, and yaw, you'll see that the matrix actually simplifies to what you saw here. Again, you'll observe that there is this minus sign is there on one side, but it's not there on the other side, indicating that this matrix is skew symmetric. Okay, again, as we looked at the last class about the linear approximation about the operating point u equal to capital U and all of the modes being 0, this leads to a simplification MRB times V dot plus CRB star times V is equal to tau B, where the CRB star is a linearized Coriolis matrix, and it can be shown that in this case the Coriolis matrix turns out to be 0, 0, and then 0, MU and MXGU. You can actually see that indeed, if I look at the CRB matrix and I understand that what is happening to the terms if I multiply by U, V, and R, and you'll see that minus mr times V will become 0 because that will be a nonlinear term and the values will be very small. So because we are operating about the delta point, U equal to capital U plus delta U, V is equal to delta V, and R is equal to delta R. So delta R times delta V will be small. Similarly, in this case, delta R square will also be small. So what will be left really is these two terms. So this term is M times U times R. So that is what will be left here, MU. And the next term will be mxgr. So this again term will be multiplied by u. So what will be left is mxgu. Mxgu is what you see here. Is that making sense?
Yes, sir.
Yeah, because this thing will now be multiplied by u, v, and r. So we should get the same terms as what we had before. Again, you can clearly see that CRB star is no longer a skew-symmetric matrix. So this is not equal to its negative of its transpose. So it's no longer skew-symmetry is no longer maintained when we perform the linearization. Okay. Now, when the vessel operates in the calm water, so far we have only looked at the rigid body dynamics. So let's try to understand the concepts which we need to capture when we are dealing with the maneuvering modes. So now we are talking about a vessel that operates in the calm water, and so therefore that the inertial forces are not just contributed by the body, but also by the fluid, which means that as the body is oscillating or moving some performing some motions, so is the fluid surrounding to the body also experiencing some displacements. So that amount of fluid, that notional amount of fluid which is actually engaging with the body in its dynamics is called the added mass. And then there is also a loss of energy, because in the sense when my ship is undergoing some motions, it is generating waves which are propagating away from the body. So those waves which are radiating away, they are taking some amount of energy off of the system, or the energy which was created, which was required to create those waves is something which has been dissipated from the ship's motions. So that part is called radiation damping, and that is particularly important. So here this is not out of viscous origin, but rather this is coming out of potential theory. Okay. Is everybody with me on radiation damping?
Yes, sir.
Yes. Okay. All right. Notice that the radiation damping generally tends to 0 for the horizontal modes. That is because that when we are looking at the horizontal modes, we are really looking at operations which are really slow. Okay, and at very low speeds or very slow motions, you don't tend to set off very large waves, right? If you move it very quickly, you will generate generally larger waves. But if I try to move it really slowly, I don't expect to see huge waves come into the picture, or at least don't expect to see large radiated waves come into the picture. And that's why this radiation damping typically tends to 0 for most of the horizontal modes motion, because we are looking at very slow motions when we talk about maneuvering. So therefore, in order to consider the dynamics precisely, what we find is instead of the radiation damping, the viscous damping becomes important and must be included when we are modeling the maneuvering modes. In contrast, when we are looking at the so-called sea-keeping modes or the so-called station-keeping problem, The radiation damping really typically has a much higher damping value. So if we look at what is its value in heave, roll, and pitch, you will find that these three modes generally will have quite a lot of radiation damping because of the stiffness and the what you call the waves that they generate will be larger. But whereas when we are looking at the so-called horizontal modes of motion, you don't tend to really bring out huge waves. So therefore, their radiation damping values tend to zero as we are looking at slow motions. But the same can't be said when we are looking at the higher frequency sea-keeping modes in heave, roll, and pitch. So in that case, many times you may want to neglect the viscous damping because the radiation damping is pretty much large. But when you're looking at cases where the radiation damping is particularly low, you might be more interested in actually capturing the viscous damping into the dynamics so that your response amplitudes that you observe have some semblance of matching with what happens in the reality. Is everybody with me on this? Yes, no?
Sir, does roll motion really contribute a lot of radiation damping?
Correct. So for ship-shaped structures, yes, roll is another case where you may find that the radiation damping is relatively lower at the roll natural frequency. So there too, you might be required to compute the viscous damping effects to be significantly higher. That's right. But typically, for most smaller ships or what you call not large ships, you'll find that even the roll natural frequency will not be lying well out of the wave frequency regime, and the radiation bank damping is sometimes significantly good enough.
Okay, sir.
Okay. All right. Okay, so the horizontal modes of a marine craft with a port-starboard symmetry can be described using a zero frequency model when we consider the so-called added masses, because those motions are of large time order. So which means that we are really looking at something close to zero frequency. So we can approximate it as a zero frequency case. So in this case, our added mass matrix typically will become the values sampled at zero frequency. And typically you will not see much of a coupling between the surge mode and the sway mode, similarly between the surge mode and the yaw mode. However, the sway and the yaw are typically coupled, so therefore you will see that these cross-diagonal terms are generally non-zero, whereas the surge is kind of somewhat decoupled from the sway and the yaw. Notice that in a real case scenario where we are actually looking at sea-keeping motions, this thing was frequency dependent, right? And we wanted to kind of capture it depending on which wave frequency is coming at us. We want to look at what is the added mass that we need to consider. But when we are talking about the so-called maneuvering, we are really looking at low frequency, slow motions. So we can approximate this by a zero frequency model, and that will save us some effort in trying to simulate the motions by disregarding the so-called frequency effects or the so-called uh, impulse response function effects. Those can be neglected when we are looking at the maneuvering motions. Is everybody with me so far? Yes, no? No? What is not clear?
The last portion that you said isn't too clear for me.
About the added mass?
Yeah, the zero frequency model, the merge can be used.
Okay, so typically your added mass is a function of frequency, right? So you
Yes.
have m plus a omega times the so-called the acceleration plus the damping, which is also dependent on the frequency, times the v plus the so-called stiffness matrix times the displacements, which I in this case call this. So I can call this v as zeta dot and v dot as zeta double dot, and that's equal to the force. This is something which you have seen in the sea-keeping model, isn't it?
Yes, sir.
So here these quantities are frequency dependent. So which means that now if I want to analyze it in the so-called time domain, I can't directly use this differential equation, isn't it?
We have to convert the frequency domain.
Yeah, either I have to convert things back into the frequency domain or I have to convert my equations of motion into the time domain. So can't be directly applied, and usually that is where you will end up with a so-called impulse response function. So you can quickly give an overview of it. We'll not discuss this too much because this is well outside the scope of our course, but since we have brought it up, let's have a brief talk about it. So let's say that we have zeta double dot plus the damping matrix times zeta plus the stiffness matrix times. Now the convention may be different. Sometimes you might call this K instead of C. I'm just going with this convention, okay? But all of you, I'm presuming, have seen this equation of motion somewhere or the other. The undergraduates more so in their ship motions course, and the graduates in their statics and dynamics course.
Yes, sir.
Yes, everybody has seen this. Okay, fantastic. So if this I can apply. So for example, if this I am looking at a wave elevation of a cos kx minus omega t, which is a single frequency progressive wave, then I know that my F, which is the external force, will also be a function of that frequency, correct?
Yes, sir.
Right? Or in other words, if I write this in the so-called complex form, I can write this as e to the power I minus kx plus omega t, something like that. Correct. So this means that my F vector is nothing but some F naught amplitude times e to the power I omega t. I'll get that e to the power I omega t variation in it. So it means that I can actually assume that my displacements, since this equation is linear, I can assume that the displacements also have some amplitude times e to the power I omega t is a possible solution of that differential equation. Yes?
Yes, sir.
And then you substitute this into here, and that gives you that so-called minus omega square m plus a of omega plus I omega b of omega plus c whole thing multiplied by the displacement amplitude is equal to the so-called force amplitude, right? And then I can actually take an inverse of this and multiply it on either side. So I'll get zeta naught is equal to this whole thing inverse times 0. Now, what do we call these things? If I assume that the amplitude of these waves is equal to 1, then what I get as the amplitude of the motions, what do we call these? Everybody's following me, yes? No? Is there a confusion on this?
No, sir. Is that the amplification factor? Uh,
This is called the RAO, response amplitude
RA
operator.
amplitude operator, yeah.
Response amplitude operator. And that's the RAO. But I'm surprised that people are not very actively responding on this. Is this not something which you have seen before?
Yeah, I
Aditya,
forgot it. Yeah.
Yes.
Aditya, Vallabh, Anand.
Yes, sir.
Yes, sir. Like kind of, we have to revisit this. Forgotten a bit.
You've forgotten about it. Okay. All right. So in this case, we are basically dealing with one frequency at a time. That's the idea, that our wave is a so-called regular wave. And that's what we are trying to put it. But the idea is that if I want to extend this to an irregular wave, so let's say that my eta of t is no longer represented by a regular wave, but it's a random wave. Something like that. Okay, that's a very bad wave that I have drawn, but nevertheless, let's just say. So if that is equal to some random wave, we can't directly calculate f for it. Why not? Because the point is that even if we calculated, let us say f for it, so I say for this random wave, I calculate what the force in time looks like. Let's imagine that we did. Okay, I still can't solve this differential equation straight away, because what added mass frequency should I choose? What radiation damping frequency should I choose? There's no clarity on that, isn't it?
Yes, sir.
Right? So in order to actually be able to convert this and be able to solve it in time domain, we need to do a conversion. So what we do is actually we take this so-called radiation force, which is A of omega times zeta double dot plus B of omega times zeta dot, and we take the so-called Fourier inverse of this to convert this into time domain, so that we can actually apply this in time domain. So that when I know f of t for the random wave, I can just solve this differential equation. Right now I can't solve it because I don't know what A to use or how to handle the fact that I know it for different frequencies, but my input signal now is not of one frequency, but it's coming due to hundreds of different frequencies combined together. Is that making sense?
Sir, can you explain the last part?
Yes. See, this if I know the for a random wave, let's say I'm able to calculate the force in time. So I have a time history of force known to me. I want to calculate the displacements with respect to time. That is the problem. Okay? And the point is, can I use this equation which you see here? Can this equation be used to solve the displacements directly? My contention is we can't directly use it because I don't know what frequency to use from here.
Yes, sir.
Right? There is a confusion as to how to deal with it, because this so-called frequency is only applicable when I am talking about a regular wave. But now it's not a regular wave, it's a random wave. It has so many frequencies coming at it together. So how do I solve it? That becomes the question. Now, one way would be to actually take a Fourier transform of your wave elevation, convert it into a series of regular waves. So which means that if I have the so-called irregular wave, I will say that this irregular wave is equal to sum of regular waves of different frequencies. So on and so forth. I may have something like that. So I just add all these regular waves in order to get the so-called irregular wave. And this process of decomposition is called Fourier transform, right?
Yes, sir.
So I'm basically looking at what are the Fourier components in a signal. And for now that I have each regular wave, I can compute this differential equation for each regular wave to find out what is the response, which also will be regular for each case, correct? Because if the input is a regular wave, the output also will be a regular wave. That's what is our assumption, right? As long as the system is linear.
Yes, sir.
Now, therefore, let's say that this is my f of t, and this is f1 of t, f2 of t, f3 of t. So f of t is equal to f1 plus f2 plus f3. Now, for each of these, I can compute what the response looks like, let's say. Okay, so I'll call these zeta 1 of t, zeta 2 of t, zeta 3 of t. And when I add them all up, I should get some random response of the system, which I'll call zeta of t. Okay, so what I'm doing, I'm actually taking the original time history of the wave, breaking it up into regular waves, calculating the forces due to each of those regular waves, calculating the response of each of those regular waves, summing all of them together to get the actual response in irregular waves. This is the process which most of you have studied in your statics and dynamics or in ship motions, correct?
Yes, sir.
Yes, sir.
Yes, sir.
Now, there is a counterpart to this. So instead of doing this transformation into frequency domain and then computing the response in frequency domain and then computing the total response, I can actually try to solve the differential equation directly. But clearly, I can't solve this differential equation directly because I don't know what to do about these terms. Correct?
Yes, sir.
Now, the way to go about them is to take a Fourier inverse of this so-called A omega zeta double dot plus B omega times zeta dot and take a Fourier inverse of it to convert this so-called expression, which is in frequency domain, it is dependent on frequency, into the time domain. And when I take that, what I get is I get something called A infinity matrix, which is the infinite frequency added mass, plus I get a convolution term, which turns out to be this pointer. Yeah. Integral minus infinity to t, k of t minus tau times zeta dot d tau. So instead of having the A of omega and B of omega, I now have something called A infinity and this big matrix looking K. Now these K matrices are what are called impulse response functions. Or IRFs. Or these are also sometimes called retardation functions. So which means that my new equation of motion, which is only dependent on time. So unlike the equation of motion here, which is half dependent on time and half dependent on frequency, the full thing simply becomes m plus a infinity times zeta double dot plus a convolution integral of this K matrix times zeta dot at time tau d tau plus the rest of the terms remain the same. C times zeta is equal to f of t. So notice now what is happening. There is no dependence on frequency on the left hand side. So I can actually find out what my force is as a time history, directly plug it in and use a solver like ODE45 in MATLAB to solve this differential equation directly to get what my zeta looks like. The only difference being that this convolution means that I need to know the history of what happened in the past. I need to know what is the history of the displacement or the velocity vector. Because tau is ranging from minus infinity to t, it means that what happened in the past does have an effect on what is happening now. Is that making sense? What I mean by how the past is affecting the current step?
Yes, sir.
Right? So this part is what is called the memory of the fluid. Okay, because how the body moved in the past does affect the current time step. So you can think of it like this, that there is a pond in which you threw a pebble and then it generated waves, right? Which are outward moving. So even though the pebble is at the bottom of the pond, you still are seeing some waves ripple and come towards the shore, which means what happened 2-3 seconds ago when the pebble actually touched the water still continues to have an effect in the terms of the propagation of those so-called waves. Correct? Right? Even after the pebble has sunk down, we still are seeing those waves come back out. So which means that there is some memory which the fluid remembers that what happened in the past, and because of which what is the energy transformation which is carrying those waves to the shore. So that effect in the so-called time domain would be written in this form. Notice that this K matrix actually is computed from the radiation damping and added mass. And I'm not going into how that is computed for now, but just remember that it is coming by a so-called Fourier transform of these quantities. That's what we saw here, right? We're taking a Fourier transform of this thing to yield that expression for K. And this equation, which you see here in the time domain, is called the Human's equation. Which means that we now can directly solve this differential equation without having to worry about breaking apart a irregular wave into a regular components. We can directly compute the solution. Is that making sense? I know it can be a little lot to take in, but at least is the idea clear as to what is happening?
Yes, sir.
Right? Okay. And when we are looking at some program like Hydra is actually using this formulation to solve the equations of motion. So you actually require a calculation of the impulse response functions, and then those are actually used in the computation of the actual displacements which you see. In fact, Hydra goes a step further in the sense that you're not just looking at the linear equations, the inertia terms and the Coriolis terms are also captured into it. Okay?
I have doubts.
Yes.
Sir, the effect of some disturbance reduces as the time increases, right?
Effect of the disturbance?
Reduces as time goes on increasing.
Correct. So something which happened far in the future, far in the past, will have lesser effect now compared to what happened recently in the future.
Yes, sir. So will this equation take care of that?
Yes, yes, it will take care of that. Typically, these K matrix K of T will look something like that, which means that what happened just now will have the highest impact. As we go into the past, the effect is reducing.
Yes, sir.
Okay, so these typical K functions, K of T, will look something like this. Okay. Just give me a second. Hello? Yeah, I'm in class right now. Yeah. Okay. Okay, did this make sense? What we are doing with the K functions and how that is taking care of the effect of the past?
Yes, sir.
Yes.
Okay. All right. So now typically if you wanted to actually consider the so-called Coriolis matrices as well, you would have had to do something like m plus a of infinity times the v dot vector plus the CRB, or the so-called C matrix, which is the Coriolis matrix in this case, and then that times B plus this convolution integral plus the stiffness matrix times displacement is equal to the external force. Something like that you would have had to solve ideally. But the point is, we don't need to do this convolution integral so much if the motion of the body is relatively slow. So you can think of it like this. If I throw the pebble into the pond, I'll get bigger waves. Rather, if I take the pebble close to the surface of the pond and I drop it slowly, the amount of ripples generated will be lower. Does that make sense?
Yes, sir.
So if I drop it from a height versus I drop it very close to the water surface, the number of ripples, the amplitude of the ripples will be lesser in the case when I drop the pebble closer to the water surface. So as long as the motions are slow or not really large, you don't expect to see these large radiation waves come into the picture. So if I assume that my ships are moving slowly and that these waves are not really large, I can get away with the fact that I don't need to do this computation. And what I'm saying is I'll go back to my original equation, m plus a of omega times zeta double dot plus b of omega into zeta dot plus c times zeta is equal to f. I'm saying I'll go back here and I'll make the assumption that the motions are relatively small when I'm talking about maneuvering systems, which are typically of the order of 100 to 200 seconds, right? So if I'm looking at motions which are of the order of 100 to 200 seconds, what is 2 pi by 100? How much will this be? 0.06 radians per second, right? So it's already a small value, which is kind of tending closer to zero as these time periods are becoming larger. In fact, if I go for 200 seconds, you'll see that this value comes down to 0.03. right? So instead of actually considering that the frequencies are changing, as long as I say that my motions are relatively slow and I tend to keep them slow, I'm not trying to fasten them out, I can approximate this equation by, instead of considering omega, I'll simply take omega equal to 0. So in which case, my new equations of motion will simply be m plus a of 0 frequency, zeta double dot, plus b of 0 times zeta dot plus c times zeta is equal to f. Is that fair enough? As long as the motions are slow. That is a good assumption which I am taking. Can I say this?
Yes, sir.
Yes, sir.
Now, the moment I say this, what has happened? There is no frequency dependence here. I can directly solve this equation itself in time domain. I don't need to do any more convolution things, right?
Yes, sir.
So that is what we are doing here. So when we are talking about the slow motions, let me just erase this thing here. Need a bigger eraser. Okay, all right. So what I'm saying is that the added mass damping, the so-called added mass, I'll consider that at 0 frequency. So I'm considering the forces or the added masses at the 0 frequency. And you'll typically see that the surge and the sway and yaw are not really coupled. So these values will be, they may not be exactly 0, but they'll be pretty close to 0 in a real computation. So you can as well ignore them. It won't change your dynamics by a significant amount. But you can't ignore these cross terms, A62 and A26. They do need to be included. That is the idea. Okay? I hope I'm making sense now.
Yes, sir.
Okay, all right. Now the idea is that this is so-called good for a 3 degree of freedom system, and the damping matrix also I can take it in a similar way, but you'll actually see that these damping matrices at 0 frequency will be close to 0. You can verify this on your own using either Hydra or any other program which you want to, of your own choice, as long as we are coming close to 0 frequency. 0 frequency means that it's really, really slow. So it is as if I am lowering the pebble into the pond at an infinitely slow pace. So when I do it at an infinitely slow pace, I don't expect to see any waves be generated at all, right? In the limiting condition.
Yes, sir.
So when there are no waves, there is no energy being taken away. So the damping terms typically become 0 as we move towards omega equal to 0. Is that making sense? Why this will be a 3 cross 3 0 matrix?
Yes, sir.
Okay. Now, suppose I wanted to extend this to 6 degrees of freedom, because I wanted to have the roll, heave, and pitch in there somewhere, then I'll have to be careful. I can assume that the so-called surge, sway, and yaw are at 0 frequency, but the same cannot be assumed for the heave, pitch, heave, roll, and pitch. I'll need to consider these values at certain frequencies called omega 3, omega 4, and omega 5, which are nothing but the so-called natural frequencies of heave, roll, and pitch. Because typically for a system, you would really be interested in motions. The motions will be larger when the resonance is happening. So I might as well make an approximation that instead of considering these values at 0 frequency, since these are will be having significant motions, I'll consider them at the natural frequency of heave, natural frequency of roll, and natural frequency of pitch. So if I did want to extend this into a 6 degree of freedom model, but still be able to keep my added mass matrix independent of the frequency, I can do it in this way. Now, remember that this is not varying with the wave excitation. I'm fixing these at the natural frequency of heave, roll, and pitch.
Yes, sir.
Okay, that is the idea. Similarly, at that time, I'll also have to pick out the damping matrices. So you'll see that actually these need not be zeros. These values need not be zeros. You'll see that the damping in the other modes is all zero, but the heave, roll, and pitch at the natural frequency, definitely the damping will not be zero. And you'll see some values come up into your matrix. So if I wanted to extend that so-called 3 degree of freedom model with an added mass component included. So far when we started out in the beginning, we were talking about the case where we were only looking at rigid body equations. We had no added mass consideration. So what we are doing today, or what in essence we have done today, is to try to understand that when the added mass comes into the picture, when we do get the added mass into the picture, we typically want to take them at zero frequencies for the horizontal modes and at the natural frequencies when we are coming to look at the heave, roll, and pitch, or the so-called vertical modes of freedom. Now, once we know that there is an additional mass matrix coming into the picture due to that added mass, it also will have a corresponding Coriolis matrix, isn't it? Just like the regular mass matrix has a Coriolis matrix corresponding to it, we would expect to see the added mass matrix also have a corresponding Coriolis matrix. Isn't that right?
Yeah, let's.
Right. So we'll have to find out what that so-called Coriolis matrix for the added mass looks like. And I'm going to take that up in the coming lecture when we meet on Monday. So on Monday, we'll talk more about what happens to that added mass matrix version of Coriolis matrix. We'll try to derive that. We'll not do an explicit derivation, but at least try to get a physical understanding of what is happening with it and how do I model that into my maneuvering models. So that's what we'll take a look on Monday. Any other questions before I close down the recording? No other questions?
No question, sir.
Okay, in that case, we'll stop recording.